All right, so here we're going to take a little example looking at limiting reagents and percent yields and figuring out how much remains at the end of here. So really this problem is taking everything that we've been doing in this chapter and putting it all into one big old problem. All right, so there's many parts to this and we'll look at each little part individually as we go along. Okay, so first up, here's our problem. We have 100 grams of nitrogen and 25 grams of hydrogen. And we mix these at 350 degrees C and, let's say 500 atmospheres of pressure. And then we form 28.96 grams of ammonia. That's our reaction. And what we want to figure out is, well, what is the percent yield and how much nitrogen and hydrogen remain. We're taking nitrogen, hydrogen, mixing them together at high temperature and pressure, and out of this we get this many grams of ammonia, so we're just trying to figure out, well, what is our yield, and also how much nitrogen and hydrogen from the original reaction are actually still going to be around. So, a bunch of parts to this. First off, before we start anything, we always need a balanced equation. We're going to have here nitrogen plus hydrogen gives us ammonia. All right, now of course we have to balance this, so I have here 2 nitrogens, 1 nitrogen, so I'm going to need a 2 in front of that. Here I have 6 hydrogens, there I have 2, so I'm going to need to put a 3 in front of there. All right, so again, we do have different coefficients for this, but here we only have one product, so that makes our lives a little bit simpler for this whole problem. First up, what do we have in the problem? We have here 100 grams of nitrogen. For the hydrogen, we have here 25.0 grams, and then for the ammonia, we have 28.96 grams of the ammonia. This is a limiting reagent problem. It's also a percent yield problem, so we can't just say, well, the 100 grams all converts over to here, or the 25 all converts to here. So we're going to have to calculate each of these things individually to figure out exactly how much ammonia should be and is actually produced. All right, the next thing we're going to need, of course, is our molecular weights. So nitrogen, that's going to be 14 times 2, that's 28 grams per mole. Hydrogen, that's 2 grams per mole, and ammonia is going to be 17 grams per mole. First thing, we just need to figure out, well, what is our limiting reagent? So we'll start off here with the nitrogen. So 100 grams of nitrogen, use our molecular weight. So that's 1 mole of nitrogen, 28 grams of nitrogen. And then using our mole ratio, again, we always have to remember to use the mole ratio, so figure out how many moles of ammonia are produced. That's going to be 2 moles of ammonia is to 1 mole of nitrogen. We have that, and this works out to be 7.143 moles of ammonia. And then we do the same thing here with the hydrogen. So that's going to be 25.0 grams of hydrogen, and 1 mole of H2 is 2 grams of H2. And then here we have 2 moles of ammonia to 3 moles of hydrogen. So we calculate this out and we get 8.333 moles of ammonia. Here are my 2 predictions. Of course, since we're dealing with a limiting reagent, we go with the one that produces the least amount. So right here, this means that my nitrogen is limiting. So my nitrogen here is limiting because this is the smaller one. So that means if nitrogen is limiting, that means, of course, that my H2 is in excess. And also, just step back and look at these numbers. If we were just looking at this at a pure weight perspective, you would say, well, 100 grams of nitrogen, 25 grams of hydrogen. Obviously, hydrogen is going to be your limiting reagent because you have 1/4 the amount of hydrogen, in terms of weight or in terms of mass. But as we can obviously see, if we use here in terms of, especially when we have our stoichiometric ratios, that can always throw things off as well. But here, we can very easily see that nitrogen, even though we have more mass, will produce less amount of ammonia here. So that's, we just always have to be careful. It can be very tricky with those kind of questions. So, just be aware how much we actually are producing here. So we know what our limiting reagent is. Now we can go and figure out, well, how much ammonia should be produced. So we're going to use this value here, and we're going to go and say 7.143 moles of ammonia times 17 grams of ammonia is 1 mole of ammonia. And we calculate this out. We have here 121.4 grams of NH3, and this is the theoretical. Okay, so theoretically, if all of the ammonia was produced that the hydrogen could produce there, we would get 121.4 grams of ammonia in theory. Now, in actuality, we got significantly less than that. We only got 28.96 grams, and there's nothing wrong with that. A lot of times people start thinking, small yields means you did something wrong. Sometimes it's just the nature of the reaction. So if this reaction really isn't favored to produce ammonia, you get a small yield. You just have to do the reaction over and over and over again. So it's not necessarily the reaction's fault or anything. It just could be the nature of the reaction itself. So this is our theoretical yield. Here is our actual yield. So we just take the ratio of those to figure out our percent yield. So right here, that's going to be 28.96 grams actual over 121.4 grams theory, and then multiply by your 100% if you need to remember to put that in there, and this gives us 23.85%. Technically that would be correct to the correct number of sig figs, but when we're dealing with percent yields, I mean, if you happen to put it here as 24%, that would still be fine, because sometimes when you're dealing with these yields, there's other errors that kind of creep in, and it's not really accurate to stick that many sig figs on these things. So we got about a 24% yield, which is fine. Okay, so that's the first part of the question. What is my percent yield? Now we also have to work out how much nitrogen and hydrogen actually remain after this reaction. So what we want to do here is say, well, if we're trying to figure out how much nitrogen and hydrogen remain, that means we have to go through here and figure out, well, how much nitrogen and hydrogen actually reacted to form this amount of ammonia, right? So this was my actual yield. Well, that means we just have to work backwards and figure out how much nitrogen and hydrogen actually underwent this reaction here. We're going to start off here with my 28.96 grams of ammonia. So that's what was produced. And then we're going to convert this into moles. And then we're going to use our mole ratio. So we're going to start with the nitrogen here. So I have 1 mole of nitrogen to 2 moles of ammonia. And then we'll use our molecular weight of our nitrogen. It's going to be 28 grams of nitrogen per mole of nitrogen. So there's nothing weird about starting off with the product and figuring out how much reactants we need. The math is still the same. As long as my grams of ammonia cancel, moles of ammonia cancel, moles of nitrogen cancel, grams of nitrogen's left over. It all works out. So we run through these numbers, we do our calculation, and we get here 23.85 grams of nitrogen used. And sometimes it's just important to put here nitrogen used, so this way nitrogen used, nitrogen started with, just to keep track of these things in your head. All right. And then the second thing we're going to do is figure out how much hydrogen was actually used here. So it's going to be exactly the same thing we started with. So we'll have 28.96 grams of ammonia. So that's exactly the same. And then over here we're going to have now 3 moles of hydrogen and 2 moles of ammonia. And then our 2 grams per mole. So we run through this calculation and we get here 5.11 grams of H2 used. And as a little double check, just to make sure you did all your math right, if I add here my nitrogen and my hydrogen, that should equal the mass of the ammonia. So here 23.85 plus 5.11, and these of course grams, is equal to 28.96. Right? 1 plus 5, that's 6. 8 plus 1 is 9. 23 plus 5, that's 28. Okay. So here, that's my nitrogen plus my hydrogen is my NH3. So mass is conserved, so you did your calculation right up there. Now we just wanted to figure out, well, how much nitrogen and hydrogen actually remain. Well, remember, this was the amount used. This was the amount we started with. So we just subtract the amount we started with minus the amount used, and that's the amount that remains. So that's going to be 100.0 minus 3.85. So that's going to be 76.15 grams of nitrogen remain. And then down here, that's going to be 25.0 minus 5.11. So that's going to be 19.89 grams of H2 remain. And really, if you're looking at this, we should do this to correct sig figs. So really, you would write that as 76.2 grams N2, and that would go as 19.9 grams of H2. And these are the ones that remain. That's the basic thing behind all of this. Okay, so just to recap here, we started off by mixing 100 grams of nitrogen and 25 grams of hydrogen. We made a little less than 29 grams of ammonia. We went through, figured out what our limiting reagent was, and we figured out that, even though there's more mass of nitrogen, it still produces less moles of ammonia. So this is going to be my limiting reagent right here. We then took that limiting reagent, figured out how many grams of ammonia that actually is. And so that's my theoretical yield. Then we just took our actual yield that we had over my theoretical to figure out my percent yield. And then down here we could just figure out, well, how much, to make this amount of ammonia, how much nitrogen and hydrogen were actually used. So we figured out there. And then we subtracted off the amount that was used from the amount that we started with to give us the amount that remains. And then we just put that to the correct number of sig figs right there. So that's the end of that problem.